stars like our own sun form from gas clouds that have about every kind of element there is, as well as some pretty complicated molecules. Stuff left over after the sun forms usually turns into a system of planets. Some of these planets have a solid surface, perhaps liquid seas, and a gaseous atmosphere. A rich environment for atoms and molecules to come together in a complex chemical reaction. Carbon atoms in particular link together to form complex organic molecules and amino acids. Chemical catalysts speed reactions along. The products of one chemical reaction become the raw material for new reactions. At some level of complexity, a catalyst becomes an enzyme. An amino acid chain becomes a protein. A loop of chemical reactions become a metabolism. And chemistry becomes biology. On our planet, and perhaps countless others, life arose. The DNA molecule, which is the basis of all organic life on Earth, is more intricate by far than any spiral galaxy, because the structure of DNA contains something new, something that was missing from inanimate matter before the origin of life. It contains information. The DNA molecule encodes not only the information necessary to make copies of itself, but the information necessary to construct an entire organism. The blueprints for an ant, or a dolphin, or a bullfrog, or even a person. All of this information is somehow built into the structure of an organism's DNA in a molecular code billions of letters long. This information wasn't always there. The first DNA molecules could probably do nothing more than make copies of themselves from the surrounding molecules. This self-reproduction is a fundamental aspect of what we call life. And once there was life, a new set of rules took over. The laws of natural selection. Life became matter that evolved as a result of environmental pressures. Matter that changed randomly. But those changes only endured if they improved a life form's chances of survival in each environment. Change with a purpose. While a species' evolution is determined by the interaction of random changes and environmental pressures, changes in an individual life form can be the result of an organism's reacting and adapting within its own sphere of influence. It can push back at its environment. The better a system was at making copies of itself, the more copies there were in the next generation. As the first living organisms adapted to ever-changing environments, a greater diversity of living things arose. A side effect of this increase of diversity was increased complexity. Now, all of our tests point ever more towards the complex end of our complexity meter. Consider a living single-celled organism. There's nothing reversible about life or death, or eating or being eaten. And there is uniqueness. Unlike electrons that are interchangeable, even single cells are absolutely unique. They may be capable of the same functionality, but they are always different in form and structure. Single cells soon join together to form multicellular colonies. And cells in these new colonies, once functionally interchangeable, became increasingly specialized. Some cells did the digesting, others became responsible for movement. Specialized cells led to the specialized tissues and organs. And most importantly, cells that could respond to light, or electricity, or chemical disturbances evolved into full-fledged nervous systems.
Hey Jeeves, I noticed that this section doesn't discuss the origin or development of inorganic life, such as yourself.
Not only that, it claims that self-reproduction is a fundamental aspect of all life. Jeeves, do you reproduce? Do you have offspring?
Good questions, but not now, please. We still have a great deal of ground to cover, and we have good reason to maintain our focus on organic life.
I agree, Chaucer, but I would love to have that conversation with you two at another time, Kevin and Diana. For centuries, the standard approach of science has been to understand nature by breaking it down into smaller and smaller pieces. Consider a flower. If we were to study flowers in their natural environment, their various forms and features, that makes us botanists. But in order to really understand how the flower works, how photosynthesis keeps the flower alive and allows it to grow, we have to get inside the flower. We might then study the cells that make up the flower, how the parts of the cell function, and how they are similar to cells of other living organisms. A cell biologist seeks to understand the flowers on this level. But in order to understand how the cells function, we need to understand the complex biochemistry of the cell's metabolism. And in order to understand how the flower's cells divide and reproduce, we have to understand the operations of DNA. The biochemist and the geneticist then seek to understand the flower on a deeper level. The study of organic molecules and DNA takes us down to the level of basic chemistry. How do atoms and molecules interact and combine with one another? This is the realm of the chemist. And understanding the forces at work inside atoms is the job of the physicist. Through this approach, breaking down the flower into smaller and smaller parts, and understanding how those parts function, we have built up a deep and comprehensive view of the laws of nature, from biology down to chemistry, and from chemistry down to physics. But there's a limitation with this approach. Somewhere along the way, we lost the flower. In other words, by breaking the flower down into smaller and simpler pieces, we've lost sight of the complexity that makes the flower what it is. Is there a different approach? Is there some better way to understand complex systems? Not by examining how their parts function, but by understanding how the parts come together to create something that is, in a sense, more than just the sum of its parts. Some scientists believe that order and complexity are inevitable. The study of systems as diverse as board games, computer programs, and ant colonies has revealed some remarkable features of complex systems. Rules much simpler than those of physics and chemistry can result in a great deal of complexity. Consider a board game like chess. The game is based on a simple set of rules. Even young children can learn the rules of chess well enough to play. But while the rules of chess are simple, the game is incredibly complex. It has been estimated that the total number of possible chess games is greater than the number of quarks and electrons in the entire cosmos. With only 32 pieces operating under a simple set of rules, the complexity of the chess universe is astounding. Where does the complexity of the game of chess come from? It's not the individual moves of the pieces. It's the way those pieces affect one another. The way each move depends on the previous turn. The way the possibilities multiply each time a piece is moved.